64,000 is the median number of words per book. Average person reads about 200 words per minute. Simple math will tell us that is one book in 320 minutes. To accomplish this in 7 days, numbers say you would have to read for 45 minutes a day. Don't forget to subscribe. Hit that notification button, like, comment, and share. Enjoy. Hello, and happy day. How does slowing down sound to you today? Would you like to reduce the noise for just a bit? Are you ready to make a choice and decide to listen? My name is Igor SF Walker. I'm here to remind people to slow down, to reduce the noise, to walk their lives into a natural flow. Welcome back to the Book of the Week series. Every week as I read another amazing title, I share it with the world. And today we look at The Code Breaker, Jennifer Doudna, Gene Editing, and the Future of the Human Race by Walter Isaacson. In this video, we look at how Nobel Prize winner Jennifer Doudna and her colleagues launched a revolution that will allow us to cure disease, fend off viruses, and have healthier babies. The past half century has been a digital age based on the microchip computer and the internet. Now we are entering a life science revolution. Children who study digital coding will be joined by those who study genetic code. Stick around till the end. I will share with you some tools I haven't used that will help you tremendously in this game of life. Discover a way to find out what actually motivates you, what innate human need is driving all of your decisions and your behavior. I will share some tools to improve your self-awareness, social awareness, self-management, and relationship management. Whoa! Our newfound ability to make edits to our genes raises some fascinating questions. Should we edit our species to make us less susceptible to deadly viruses? What a wonderful boom that would be, right? Should we use gene editing to eliminate dreaded disorders such as Huntington's, sickle cell anemia, and cystic fibrosis? That sounds good too. And what about deafness or blindness or being short or depressed? How should we think about that? A few decades from now, if it becomes possible and safe, should we allow parents to enhance the IQ and the muscles of their kids? Should we let them decide eye color, skin color, height? Let's pause for a moment before we slide all the way down this slippery slope. What might that do to the diversity of our society if we are no longer subject to a random natural lottery when it comes to our endowments? Will it weaken our feeling of empathy and acceptance? If these offerings at the genetic supermarket aren't free, and they will not be, will that greatly increase inequality and indeed encode it permanently in the human race? Given these issues, should such decisions be left solely to the individuals, or should society as a whole have some say? Perhaps we should develop some rules, and by we, I mean we, all of us, including you and me. The invention of CRISPR, as well as this COVID episode, will hasten our transition to the third great revolution of the modern times. These revolutions arose from the discovery, beginning just over a century ago, of the three fundamental kernels of our existence: the atom, the bit, and the gene. Now we have entered this third and even more momentous era, a life science revolution. When Doudna was a graduate student in the 1990s, other biologists were fascinated to map the genes that are coded by our DNA. But she became more interested in DNA's less celebrated sibling, RNA. It's the molecule that actually does the work in a cell by copying some of the instructions coded by the DNA and then using them to build proteins. DNA may be the world's most famous molecule, so well known that it appears in magazine covers. It is used as a metaphor for traits that are ingrained in a society or an organization. But like many famous siblings, DNA doesn't do much work. It mainly stays at home in the nucleus of our cells, not venturing forth. Its primary activity is protecting the information it encodes and occasionally replicating itself. RNA, on the other hand, actually goes out and does real work. Instead of just sitting at home curating information, it makes real products, such as proteins. Pay attention to it. At the time of the Human Genome Project, RNA was seen as mainly a messenger molecule that carries instructions from the DNA that is nestled in the nucleus of the cells. A small segment of the DNA that encodes a gene is transcribed into a snippet of RNA, which then travels to the manufacturing region of the cell. There, this messenger RNA facilitates the assembly of the proper sequence of amino acids to make a specified protein. Fibrous proteins, for example, form structures such as bones, tissues, muscles, hair, fingernails, tendons, and skin cells. Membrane proteins release signals within cells. Above all is the most fascinating type of proteins, enzymes. They serve as catalysts. They spark and accelerate and modulate the chemical reactions in all living things. Almost every action that takes place in a cell needs to be catalyzed by an enzyme. Pay attention to enzymes. Enzymes are a type of protein. Their main function is to act as a catalyst that sparks chemical reactions in the cells of all living organisms, from bacteria to humans. There are more than 5,000 biochemical reactions that are catalyzed by enzymes. These include breaking down starches and proteins in the digestive system, causing muscles to contract, sending signals between cells, regulating metabolism, and most important for this discussion, cutting and slicing DNA and RNA. By 2008, scientists had discovered a handful of enzymes produced by genes that are adjacent to the CRISPR sequences in bacteria's DNA. These CRISPR-associated CAS enzymes enable the system to cut and paste new memories of viruses that attack the bacteria. They also create short segments of RNA, known as the CRISPR RNA or cRNA, that can guide a scissor-like enzyme to a dangerous virus and then cut up its genetic material. Presto! That's how the wily bacteria create an adaptive immune system, CRISPR. It turns out that the tracer RNA performs two important tasks. First, it facilitates the making of the cRNA. the sequence that carries the memory of the virus previously attacked the bacteria. Then it serves as the handle to latch on to the invading virus so that the cRNA can target the right spot for the Cas enzyme to chop. This amazing little system quickly became clear, truly had momentous potential application. The cRNA guide could be modified to target any DNA sequence you might wish to cut. It was programmable. It could become an editing tool. The study of CRISPR would become a vivid example of the call and response between basic science and translational medicine. Once we figured out the components of the CRISPR Cas9 assembly, we realized that we could program it on our own. Doudna says. In other words, we could add a different cRNA and get it to cut any different DNA sequence we choose. The road to engineering human genes. In 1972, when Professor Paul Berg of Stanford discovered a way to take a bit of DNA of a virus found in monkeys and splice it to the DNA of a totally different virus. Presto. He had manufactured what he dubbed recombinant DNA. Herbert Boyer and Stanley Cohen discovered ways to make these artificial genes more efficient and then clone millions of copies of them. It took another 15 years before scientists began to deliver engineered DNA into the cells of the humans. The goal was similar to creating a drug. There was no attempt to change the DNA of the patient. It was not gene editing. Instead, it was gene therapy. And it involved delivering into the patient's cells some DNA that had been engineered to counteract the faulty gene that caused the disease. The field of gene therapy initially showed modest success, but soon there were setbacks. In 1992, in clinical trial in Philadelphia, came to a halt when a young man died due to a massive immune response caused by the virus transporting the therapeutic gene. In the early 2000s, a gene therapy procedure for an immune deficiency disease inadvertently triggered a cancer-causing gene that led to 5 patients developing leukemia. Tragedies such as these froze at least a decade most of the clinical trials, but incremental improvements in gene therapies would lay the groundwork for the more ambitious field of gene editing. Instead of treating genetic problems through the gene therapy, some medical researchers began looking for ways to fix the problems at their source. The goal was to edit the flawed sequence of the DNA in the relevant cells of the patient. Thus was born the endeavor called gene editing. The invention of gene editing required 2 steps. First, researchers had to find the right enzyme that could cut a double-strand break in the DNA. Then they had to figure out a guide that would navigate the enzyme to the precise target in the cell's DNA where they wanted to make the cut. Ever since the Republic of Venice in 1474 passed a statute giving the inventors of any new and ingenious device the exclusive right to profit from it for 10 years, people have been wrestling over patents. In the United States, they're enshrined in the Article 1 of the Constitution. The Congress shall have power to promote the progress of science and useful arts by securing, for a limited time, to authors and inventors the exclusive right to their respective writings and discoveries, A year after ratification, Congress passed an act that allowed patents of any useful art, manufacture, engine, machine, or device, or any improvement thereon not before known. In 1873, for example, a French biologist, Louis Pasteur, was awarded the first known patent for a microorganism, the method for making yeast free from organic germs of disease. Thus we have pasteurized milk, juice, and wine. Two major milestones occurred in the 1980. The U.S. Supreme Court ruled in favor of a genetic engineer who had derived a strain of bacteria capable of eating crude oil, which may be useful in cleaning up oil spills. His application had been rejected by the Patent Office on the theory that you could not patent a living thing. But a Supreme Court ruled in a 5-4 decision written by Chief Justice Burger that a live human-made microorganism is patentable if it is a product of human ingenuity. Encouraged by a small number of patents that made huge sums, universities developed massive infrastructure to profit from their research. We see with CRISPR the toxic effects of turning academic institutions into money-hungry hawkers of intellectual property. In the digital realm, there isn't a clear line separating amateur from professional coders. The same might soon be true for bioengineering. Despite the dangers, there could be benefits. If the biotech followed this route during a pandemic, it would be useful if societies could tap the biological wisdom and innovation of crowds. At the very least, it would be good to have citizens who could test themselves and their neighbors at home. Contact tracing and data collection could be crowdsourced. Today, there's a sharp line dividing official sanctioned biologists from do-it-yourself hackers. 2016, when James Clapper, the U.S. Director of National Intelligence, issued the agency's annual Worldwide Threat Assessment, and it included, for the first time, genome editing as a potential weapon of mass destruction. As a result, the Defense Advanced Research Projects Agency, DARPA, which is the Pentagon's well-funded research arm, launched a program called Safe Genes to support ways to defend against genetically engineered weapons. It dispensed $65 million worth of grants, making the military the largest single source of money for CRISPR research. They focused on a method that some viruses use to disable the CRISPR systems of the bacteria they are attacking. In other words, bacteria developed CRISPR systems to ward off viruses. But then the viruses developed a way to shut down those defenses. It was an arms race that Pentagon could understand. Missiles being countered by defense systems, being countered by anti-defense systems. The newly discovered systems were dubbed anti-CRISPRs. For decades, the ideas of creating engineered humans belonged to the realm of science fiction. Three classic works of what might happen if we snatched this fire from the gods. Mary Shelley's 1818 novel Frankenstein, or the modern Prometheus, was a cautionary tale about a scientist who engineers a human-like creation. In H.G. Wells's The Time Machine, published in 1895, a traveler to the future discovers that humans have evolved into two species, a leisure class of Eloi and a working class of warlocks. Aldous Huxley's Brave New World, published in 1932, describes a similar dystopian future in which genetic modification produces an elite class of leaders with enhanced intellectual and physical traits. The idea of engineering humans moved from the realm of science fiction to the realm of science in the 1960s. Even though human gene editing technologies had not yet been devised, the battle lines have been defined. It became the mission of many of the scientists to find the middle ground rather than have this issue become politically polarized. Two concerns that were present. The first was a fear that in genetic engineering was leading to increased corporate involvement in the university research. Universities had historically focused on basic research and the open exchange of ideas. These goals may run headlong into those industries, the development of marketable products and techniques through applied research by maintaining a competitive posture, protecting trade secrets, and seeking patent protection. The second concern was that the genetic engineering would increase inequality. New biotech procedures would be expensive, so people who were born into privilege would likely get the most benefits. That could widen and even genetically encode existing inequalities. The possibilities presented by gene therapy and gene surgery may in fact call into a question a central element of democratic political theory in practice: the commitment to equality of opportunity. Mercy for families in need. For few families, early gene surgery may be the only viable way to heal a heritable disease and save a child from a lifetime of suffering. Only for serious disease, never vanity. Gene surgery is a serious medical procedure that should never be used for aesthetics enhancements or sex selection. Respect a child's autonomy. A life is more than our physical body. Genes do not define you. Our DNA does not predetermine our purpose or what we could and can achieve. We flourish from our own hard work, nutrition, and support from society and our loved ones. Everyone deserves freedom from genetic disease. Wealth should not determine health. On most great moral issues, there are two competing perspectives. One emphasizes individual rights, personal liberties, and deference to personal choice. Stemming from John Locke and the other Enlightenment thinkers of the 17th century, this tradition recognizes that people will have different beliefs about what is good for their lives, and it argues that the state should give them a lot of liberty to make their own choices as long as they do not harm others. Now, the contrasting perspectives are those that view justice and morality through the lens of what is best for society and perhaps even, in the case of bioengineering and climate policy, the species. The emphasis on societal benefits rather than individual rights can take the form of John Stuart's known utilitarianism, which seeks the great amount of happiness in a society, even if that means trampling on the liberties of some individuals. Or it can take the form of more complex social contract theories, in which moral obligations arise from the agreements we would make to form the society we want to live in. On the one side are those who wish to maximize individual liberties, minimize regulations and taxes, and keep the state out of our lives as much as possible. On the other side are those who wish to promote the common good, create benefits for all of society, minimize the harm that untrammeled free market can do to our work and our environment and restrict selfish behaviors that might harm the community at large. Our respect for nature and nature's God should indeed instill some humility about meddling with our genes. But should it absolutely forbid it? After all, we, Homo sapiens, are part of nature, no less so than bacteria and sharks and butterflies. And through its infinite wisdom, or blind stumbling, nature has endowed our species with an ability to edit our own genes. If it's wrong for us to use CRISPR, the reason cannot merely be that it is unnatural. It is just as natural as all of those tricks that bacteria and viruses use. If we humans find ways to rig the natural lottery and engineer the genetic endowments of our children, we will be less likely to view our traits as gifts that we do accept. And it would undermine the empathy that comes from our sense, there, but for the grace of God go I, towards our fellow humans who are less lucky. What we drive to mastery misses and may even destroy is an appreciation of the gifted character of human powers and achievements. Sandel writes, to acknowledge the giftedness of life is to recognize that our talents and our powers are not wholly our own doing. Fathoming the wonders of life is more than merely useful. It is also inspiring and it's joyful. That is why we humans are lucky that we are endowed with curiosity. And maybe that instinct, well, that pure curiosity is what will save us. And there you have it. The code breaker, gene editing, and the future of the human race. Please do help out. It is easy. Simply like this video so more people can enjoy it. Share it too and spread the word. Leave a comment and share your thoughts. Subscribe to my channel and stay up to date. And the link to this book is in the description below, so buy it and read. Never stop learning, especially learning about yourself and nature. So gift yourself by taking the free human needs test on my website and find out what actually motivates you, what innate human need is driving all of your decisions and your behavior. And if you feel you are ready to improve your self-awareness, social awareness, self-management, and relationship management even further, then do check out my Master of Life Awareness program. The links are in the description below. Thank you. Love and respect.